Welcome back. In this video, we will define annuities and derive discount factors that can convert between values. The annuity is defined as a series of uniform values of cash transactions in consecutive years. So if we draw a cash flow diagram where we have on the x-axis the number of years, we have 1 year, 2 year, 3 year, and so on to n years. And on the y-axis, we will have cash flow. The annuities will be a uniform value transaction. For example, it can be going in, the values has to be the same. Suppose the values are all A for n years, n to n years also have. And this is called annuity. And in this example, we will verify that the future value f of n of annuities with each transaction value of A with n consecutive years would be expressed with this expression, and where A is the annual interest rate. For each year, we can calculate the future value f of n for year 1, f of n for year 2, f of n for year 3, and f of n for year n. And the total future value will be of n at year 1 plus future value at year 2 plus future value of year 3, and add up to the future value year n. This f of n, this n represents how many consecutive years the annuity will add up to. And for the first year, remember that the money will have its time value. So if we have a compound interest of annual interest rate of I, then we will have the original value A multiplied by the compound interest 1 plus I to the n, because it has n years. Let's suppose that we set the nth year as the basis time, because we want to find future value. So all the money's value will be converted to the final year, and therefore we will have n years to get there first year. And for the second year, we also have a base money of A, and then we compound its interest for 1 plus I for how many years? From second year to nth year, so that will be n minus 1 years. For the third year, still same base amount of money, compound interest 1 plus I, and then how many years from the third year to the nth year? That will be n minus 2, so on. And finally, we will add up the future value of the year n's money, which is just A times 1 plus I, n minus n, which is 0, so that will go to 1. And then reminder that the nth partial sum of geometric series is expressed as this, and the geometric series is equal to A R of 0, A R of 1, A R of 2, so on, and plus to the A R of n. And in this case, we have A is equal to big A that appears at each term. And then we have R is equal to everything within the parentheses, which we have exponents on. R is equal to 1 plus I. And then n is just equal to n because we're having the same n. So if we use the nth partial sum for the geometric series and convert this, we will get A is equal to A, big A, 1 minus R to the n, and R is 1 plus I. Write it as 1 plus I, and divided by 1 minus R, which is plus I. Now we can further simplify that. On the bottom, we will have just I. And we have therefore proved that the future value of annuities for each transaction value A for n consecutive years will be expressed by this value. And the interesting thing is that we notice that the future value can be expressed as the annuity value multiplied by a constant. And this constant is a function of I and n. And this will lead us to the definition of a discount. A discount factor is a conversion factor that converts money value between the past, present, and annuities. And to illustrate this concept, it is best for doing an example. For example, in the last example, we have seen that the future value can be converted from the annuity value with a constant. And if we rearrange that, we can have f of n divided by a equals that constant, 1 plus I to the nth minus 1 divided by I. And this constant is only a function of I and n. And this is called the discount factor for converting a to f. And why is it a is at the bottom and f is at the top? It is because if we want an f, then we can multiply a, which is known, by a discount factor of a, f divided by a. And this discount factor is also known if given the annual interest rate I and the consecutive years n that we are having the annuity. And since these two are known, we can calculate the things that we want, which is the future value. And notation-wise, the textbook uses a notation that is initially confusing, but after thinking about it, it is justified that they use, we have f of n divided by a, they write it as f of n divided by a, comma, I, comma, n, parentheses. And these two are equivalent because for each discount factor, it is evaluated at the annual interest rate and the number of consecutive years. Usually we write it as things like this is a function of I and n, so we write it as f of n of a is a function of I and n. And this particularly looks like it is multiplying, so that maybe that's why the textbook chose this type of notation. But I will not use that notation, and I will explicitly write out what these. Well, how do we get those discount factors or the conversion factors between different values? For example, let's derive the discount factor converting a to p. So we are given a, and we want to know p, so that we have p is wanted is equal to n given multiplied by a discount factor. And the discount factor will be a at the bottom and p top, so that we can cancel things. And therefore, the value that we're having interest in is p over a. And how do we get p over a? We do this by deriving it from known discount factor. And what discount factor do we know for now? Remember that we just derived the discount factor converting from a to f. So read it from bottom to top, converting from a to f, from annuity to future value, which is equal to 1 plus I n minus 1 divided by I. What we can do is to use a math trick. So since we have p over a, then we can write it as p divided by 1 multiplied by 1 divided by a. These cancels out, they're the same thing. But those ones, we can also write it as numbers that are the same. For example, I can have future values. The future value also cancels out to p over a. So that now I have p divided by f and f divided by a. And f divided by a we just derived here. Now we just need p over f. And P over F is just 1 plus I to the nth, because remember the formula, compound interest. Oh, I have flipped the order, 1 over that. So remember the formula for both for compound interest is that the future value is the present value times compound interest. And therefore we can have P over F is equal to 1 over the compound interest. And therefore we can plug things in. We have 1 over 1 plus I to the nth multiplied by the whole other discount factor we just did. Now we can simplify things. 1 plus I nth minus 1 I times I 1 plus I 2, where I is the annual interest rate and n is the number of consecutive years. And similarly, we can derive other type of discount factor. For example, if we want to convert from P to A, then it will be we given P, and then we want A. A equals to P times discount factor, which needs to cancel it out. So P has to be at the bottom and A has to be. This is the discount factor. And A over P, which is just the inverse of P over A. Just inverse this, get I 1 plus I to the nth and 1 plus I to the nth. Now we had derived all our common discount factor used. These two are derived from the compound interest. And these two are derived from example. And these two are derived from, and these are tabulated in the textbook table 9. And these serves as a conversion factor between the values. So for example, if I want to convert PF, remember from given to unknown, we want unknown of F equals to P times this conversion factor. To cancel out P, we want P to at the bottom and F at the top. Therefore, this is the discount factor, F over P. From given to unknown, we have given at the bottom and unknown at the top for each discount factor. So to use this table, if we're knowing what values we want, which is unknown, and know the value that we're given, then we can easily select a discount factor from this table, then plug in I and n if we know that, calculate the unknown value. Let's look at an example for using the discount factor. The example of a lottery winner will receive this amount of money per year for the next 20 years. So this is a uniform amount of money that is given in consecutive years. So a cash flow diagram will be, if this is time, we'll have constantly given the same amount of money of 2 zeros. And this is the annuity. So recognize that this amount, A equals to 250. And what is the equivalent present value? So we want P, the present value of the winning, if there is a secure investment opportunity providing I equals to 7.5% annum, which is equal to 0.07. And we have the consecutive years of 20 years, n equals to 20. So to get from known to unknown, we want P equals to A multiplied by its discount factor, which is essentially a conversion factor. A at the bottom to cancel things, B at the top. And we look back into table 9.1, we found that P of A, P divided by A, is equal to 1 plus I to the n minus 1 divided by I, 1 plus I to the n. So we substitute that in, A, and then substitute the discount factor. Now we have all the values. We have A, we have I, we have n. So substitute in. One plus 0.05. Notice do not use the percent value, use the actual numerical value. 1, 5, 1 plus 0.5. And remember n is 20, so we write the n out. Then this is a calculator's job. Will not do that. The numerical value I got is around 20389. Need to move around, comma. This is the final value for part A. For B, what rate of return? We're in part A, so what is this value? A, which is I, would be needed if we need a present value, P, which is 2.5 million. 2.5 million in value. So we still have the same annuity 250. We have P, and we still have the same consecutive years, 20. And we want to find I. And this time, we both know P, we know A, so we can either use P over A or A over P. It doesn't matter because it's known. And then since we already have the value of P over A here, let's just use that. 1 plus I to nth minus 1 divided by I plus I. And then we substitute things in. Be careful not to lose any zeros. Goes to 1 plus I to the 20th minus 1 divided by I, 1 plus I. Remember not to confuse I and 1. And this cannot be solved by hand, so we need a calculator to solve this. Now the task is easy, that we only want to numerically find out what is I. So in Desmos graphing calculator, we can plug in our expression 1 plus I to the n minus 1 divided by whole thing divided by I times 1 plus I to the n is equal to P over A. So we want to find the intersection of these where they are equal to each. So let's substitute in all the values. We have the annual interest rate I is an unknown X, and then n is consecutive years of 20. P is the present value given, which is 2550. And then A is 2 with 50. Okay. Now we have P of A and the discount factor expression. I want them to intersect, so y equals to that. We'll generate a line that intersects both of them. Then we find at the intersection we have I is equal to 0.496. And therefore, we have the annual interest rate of I equals to 0.0496. And if we want to write it in terms of percentage, it is 4.9. And if we compare these values, first we calculate it will require about $2.03 million if we have 7.5 per annum interest. However, in this case, if we have 2.5 million, then the interest rate is lower. That is because if you invest more money in it, then the interest rate will be lower. So the rate of borrowing will decrease in the same period of time, borrow more money. In this video, we defined annuity, and from the annuity expression, we derived the discount factor for various values, whether it's present value, future value, or between annuities. These can guide us to convert different values when calculating value of cash.